Hello, in this video we're going to be talking about a really important topic. Okay, and this topic is one of the most powerful tools of integration because of just how many situations it can be used. Okay, so why don't we revisit the product rule? Okay, so the product rule says that if you have two functions, f of x and g of x, and you were to take the derivative of their product, you would get f prime of x, g of x, plus g prime of x, f of x. Okay, that's our product rule. So why don't we integrate? Okay, why don't we integrate with respect to x? Okay, why don't we integrate with respect to x? So if we integrate this with both sides with respect to x, you get integral of f of x, g of x. Okay, so the integral of that derivative, that'll just be our product. That'll be f of x times g of x. So we're literally just taking the integral of all these three terms with respect to x. So f of x times g of x equals the integral of f prime of x times g of x dx, okay, plus the integral of g prime of x times f of x dx. Okay, now what exactly is, okay, so let f equals, not f, let's u, since it's a proper standard notation for this rule, let u equal f of x, and let v equal g of x, just to clean it up a little. So we have u times v equals the integral of f of x will rise u prime v dx plus v prime u dx. Okay? Now, what is u prime dx? Okay, what is u prime dx? Well, u prime dx, if you remember our lesson on differentials, that's just equal to du, because du dx is u prime. So you can write this as v times du, and you can literally say the same thing about v prime dx is dv, if you remember from differentials. So v du plus u dv, okay? And what you get if you subtract this integral v du, you get the integral of u times dv equals uv times the integral of v times du. And this marks one of the most powerful tools in integration, and that is integration by parts. Integration by parts, okay? So what this does is that it's basically like a product rule for integration, okay? And that it takes this complicated integral, and turns it into another simpler integral. So it turns into a simpler integral that hopefully that you can integrate, okay? So why don't we integrate x e to the x? So let's write the integration by parts formula again. u dv equals uv minus v du. So let's try to find x e to the x dx. So how would you find that? Okay, how would you find the integral of x e to the x dx? Well, the problem with this, okay, and one of the hardest aspects of integration by parts is to find what is u and what is dv, okay? Because you need to make a choice, okay? There's so many choices you can make. You can make u equal e to the x and dv equal x dx. The formula is not specific about which ones you have to choose. Or you can pick u equals dx and dv equals dx and u equals x e to the x. And maybe you can even have u equals x and dv equals e to the x dx. So there's so many different choices about which one you should choose, okay? But you should choose it such that this integral is easy. What does it be easy? Which means we want u, okay? We want u such that it is easier to differentiate. It's much easier to take the derivative of. And you want dv such that it's much easier to take the integral of. Okay, so the most obvious choice would be this choice. Okay, so if we were to pick u equals x and dv equals e to the x dx, then du would just be 1 times dx and v equals e to the x. So if you plug it into our formula, you get u times v minus the integral of v du. And because we chose the right one, look at this integral. It is really, really easy, okay? It is the easiest integral you could ever ask for. That's just e to the x. Okay, so through a good choice of u and dv, you get a really nice integral. And you can see that through the formula, this is actually the integral of x e to the x. What if we picked a bad choice? What happened if we picked our first choice? You would get u times v. Okay, so if u equals e to the x and dv equals x dx, then du equals e to the x dx and v equals x squared over 2. So what we would have is x squared e to the x over 2 minus the integral of v du. X squared e to the x over 2 dx. And now we just made the integral even worse. Okay, we had 1x, okay, and it was degree 1. Now we have x squared. So we in fact made the integral a lot worse. So you need to be very, very careful about which ones you pick for u and dv. Okay, such that dv, okay, it's easier to integrate. Okay, dv is easy to integrate and u is easy to differentiate. Okay, so the derivative of u is a lot simpler than u, and the integral of v is a lot simpler than dv. Okay, so let's do another one. Okay, since this is one of the most confusing lessons. So let's do the integral of e to the x sine of x dx. Now picking u and dv eventually starts to, you eventually start to get used to it, okay? And you start to know on instinct which one should be u, which one should be dv, okay? So let's make u equal to sine of x, okay? And dv equal to e to the x dx. As a rule, you never really want to make u e to the x dx because e to the x is so easy to integrate. So you usually always want to make e to the x dv, okay? Because e to the x is so much easier to integrate. So if u equals sine of x and dv equals e to the x dx, then du equals cosine of x times dx, and v equals e to the x. So let's apply integration by parts. So e to the x sine x equals, well, that's uv, so e to the x sine x minus the integral of v du, e to the x cosine of x dx. So it seems like we made it a lot worse, but turns out this is literally the only way, the most efficient way. So we're going to have to apply integration by parts again for the second integral. So for the second integral, we want to make dv equal to e to the x, just for convenience. So u equals cosine of x. That means du equals negative sine of x dx, and v equals e to the x. So we end up getting, okay, so the integral of e to the x sine of x equals e to the x sine of x minus uv, so e to the x cosine of x minus the integral of v du, negative e to the x sine of x dx. So what you can do is basically take out this negative sign, replace this with a plus sign. So that gets us e to the x sine of x minus e to the x cosine of x minus the integral of e to the x sine of x dx. So it seems like we just hit a dead end, okay? Because we're back to the exact same integral. So it seems like we're going to keep on looping around. However, you have to realize that this is an equation, okay? We have equal signs over here, and this is equal to this integral. So what you can do is use algebra. You can use algebra and add e to the x sine of x to your answer. So we're going to add this to the left. So we have 2 times e to the x sine of x. We're basically adding this expression to this. So we have 2 times e to the x sine of x equals e to the x. We're going to factor out e to the x just for cleanliness, you can say. E to the x sine of x minus cosine of x. Okay? And dividing by 2, if you divide by 2, you get this astounding result. Okay? E to the x sine of x minus cosine of x over 2. Can't forget your plus c. And that, my friends, is our integral. That is our integral. Let's do one more. Okay, let's do one more for integration by parts. And this one is, again, a integral that's similar, but different. The integral of secant cubed, which is a integral that does pop up a lot. In fact, let's not do this integral now. It is important later, but we'll do this integral a bit later. Okay? Oops, okay. Select. So let's do this integral later. So secant cubed is an integral for later, but you can do it with integration by parts. But instead, let's do the integral of ln of x, which we have all been dying for. Okay, integral of ln of x. Now, what should u be? And what should dv be? Well, if we make dv equal to ln of x dx, that's a dumb move because we're going to have to take the integral to get v. Okay? So we're going to have to let u equal ln of x. We have a dx here because that doesn't fit. So we'll have dv equal dx. And that makes sense because du, the derivative of ln of x, is just 1 over x. A lot simpler. And v equals x. The integral of dx is just x. So what we end up getting is the integral of ln of x dx equals u times v, x ln of x, minus v du. X times 1 over x, should be a dx over here, dx. This gets x ln of x minus, this becomes 1. Okay, and that gets us x ln of x minus x plus c. X ln of x minus x plus c. And we literally just finished. Okay, we're done because we picked good choices and we realized that one of dv can just equal dx by itself. Okay, dv doesn't have to have something in front of dx. dv can just equal 1 dx. And using a great choice like that really made this integral a lot easier. Okay, so now we know the integral of ln of x dx. Something that we could have been dying for. Okay, and we just found out that the integral of ln of x is x ln of x minus x plus c. So this is one of the hardest, okay? This is one of the hardest things to do, okay? Although once you get the hang of it, it turns out to be a very powerful technique, okay? Very, very powerful. So I think we should end for now, okay? Because there are a lot more integration techniques coming. So partial fraction is just one of them. Sorry, integration by parts is just one of them. Okay, so partial fraction. That is our next technique, by the way, okay? So if you have any comments, please make sure to ask. If you have any questions, please make sure to comment down below. Make sure you like this video and subscribe to our channel so we can keep on making high quality videos. Thanks for watching. Stay tuned for next time.